So let's begin by talking about some different types of numbers. The set 1, 2, 3, 4, 5, and so on and so forth are known as the natural numbers. Natural numbers are numbers that you might expect the count on Sesame Street to say. 1, ha, ha, ha. 2, ha, ha, ha. But the count starts counting with 1. He doesn't start counting with 0. 0 is not part of the natural numbers. What 0 is a part of, if we start with 0, 1, 2, 3, and so on and so forth, would be the whole numbers. So whole numbers are the natural numbers plus 0. Now, while we're talking about things today, I'll often use the letters A and B. And in this case, A and B, or any other letter you might see me use in the future, are called variables. Variables are letters which stand for any number. This would be two numbers that are the same. A equals B. This would be two numbers that are not the same. A is not equal to B. So the symbol for not equals is a slash through the equal sign. This symbol here means is less than. It's the less than symbol. Not to be confused with this symbol here, which means greater than. So if two numbers aren't equal, that means one is either less than the other, one is greater than the other. Two more symbols that we'll have in use are similar to the less than and greater than symbols, but they have this bar underneath the less than, or this bar underneath the greater than. This symbol, the less than with the bar, means is less than or equal to. So we could also use it if the two numbers are the same. It doesn't have to be strictly less than. The greater than symbol with the bar underneath means greater than or equal to. One thing that might help you keep less than and greater than straight is the idea of Pac-Man, the video game character. Pac-Man is always hungry. He's eating those dots. Pac-Man would always prefer to eat the larger number. So the big end points to the big number. The little end points to the small number. If we have a statement such that 1 is less than 3, we can say whether it's true or false, and 1 is less than 3 is true. A reason that we know that 1 is less than 3, assuming we knew nothing else about numbers, would be this thing called the number line. And right now for the number line, we're just going to look at 0 and the positive counting numbers, the whole numbers. 0 and the natural numbers. However you want to think of 0 through everything. If a number is to the left, it's smaller. If a number is to the right, it's larger. 1 is to the left of 3, so 1 is less than 3. You can think of every bit of this number line having less than signs between the numbers. We'll look at the other side of the number line in a little bit. So what are some other true mathematical statements? We can say 2 equals 2. We can say 2 is not equal to 6. These are all true statements. 3 is less than 5. 2 is greater than 0. True statements about less than and greater than can also be written in the reverse order. If 3 is less than 5, then 5 is greater than 3. Notice in both of these cases, the small pointy end points to the smaller number, and the larger open end points at the larger number. So an equivalent saying 2 is greater than 0 would be 0 is less than 2, being sure that the little end is pointed to 0 in both cases. Let's look at some examples where we need to pick less than, greater than, or equals to make a true statement. So we're going to insert a mathematical sign in between the two numbers that makes the statement true. So for 2 and 3, the proper sign would be less than. 2 is less than 3. Pac-Man wants to eat the larger number. Between 7 and 4, we would put a greater than, because 7 is greater than 4. 7 is to the right of 4 on the number line. And if we're to the right, that means we are greater. (72) and 27, again, this is a greater than. 72 is greater than 27. I'm going to put a few more examples on the board. Feel free to pause and try these. There shouldn't be any surprises. I'm going to go ahead and give away the answers now. 5 is less than 8. 6 is greater than 4. 16 is less than 82. In each of these instances, the small pointy end points to the smaller number. The large open end points to the larger number. Let's go true and false. This time we'll bring in the or equal to sign. Seven is less than or equal to 10. This would be true if 7 is less than 10 or if 7 equals 10. 7 is less than 10. That one's true. 3 is greater than or equal to 3. This would be true if 3 is greater than 3 or if 3 equals 3. Since 3 equals 3, it is true. 6 is greater than or equal to 10. This would be true if 6 is greater than 10 or if 6 equals 10. But both of those statements are false. 6 is not greater than 10. 6 is not equal to 10. That statement would be false. We have more examples. True or false still? Eight less than or equal to 8. Since 8 equals 8, this is true. And in fact, 8 greater than or equal to 8. 8 equals 8, so this one's true too. 23 is less than or equal to 0. Not true. 23 is greater than 0. False. Which means 23 greater than or equal to 0 would be true. One more batch of true, false. Feel free to pause and try these. No surprises. Nine greater than or equal to 3. Since 9 is greater than 3, this is true. Three is greater than or equal to 8. This is false. 3 is less than 8. It is not greater than 8. It is not equal to 8. 25 less than or equal to 25. Since 25 equals 25, that one's true. 4 less than or equal to 14. Since 4 is less than 14, that one is also true. Let's talk a little bit about translating sentences. Nine is less than or equal to 11. 9 is less than or equal to 11. 9 is less than or equal to 11. That's all there is to that. 8 is greater than 1. 8 is greater than 1. 8 is greater than 1. Three is not equal to 4. 3 is not equal to 4. 3 is not equal to 4. I'm going to do 3 more. Feel free to pause and try these, no surprises. Okay, I'm going to do these ones. 3 is less than 8. 3 is less than 8. 3 is less than 8. 15 is greater than or equal to 9. 15 is greater than or equal to 9. 15 is greater than or equal to 9. 6 is not equal to 7. 6 is not equal to 7. 6 is not equal to 7. And I said I'd fill in the rest of that number line. Let's do that now. We had 0, 1, 2, 3, 4, 5, 6, so on and so forth. On the other side of 0, we'll have -1, -2, -3, -4, and so on and so forth. This set we see here continuing on and on from negative infinity, -5, -4, -3, -2, -1, 0, 1, 2, 3, so on and so forth. This is the set of integers. The right side of the number line, things to the right of 0. These are positive. Let me think ahead a little bit, actually go all the way up to, but not including 0 there. Things to the left of 0 are negative. The 0 itself is neither. It's neither positive nor negative. It's just 0. Let's use integers to express numbers in word phrases. So if we were reading something and it referenced 117 degrees below 0, the integer negative 117 would be used to express that. Try this one. What integer would we use to express 10 meters below sea level? Negative 10. Back to that number line. In between the integers, there are an infinite amount of other numbers. Some of them, like 1/2, -3/2, 7/4. Some of these can be written as fractions. We refer to these numbers as rational numbers. The root of that word rational is ratio. Ratio, written as a fraction. Technical definition for rational numbers is the set of all A over B. This bar, when it's in a set, means such that. So all A over B such that A and B are integers. So if we can write a number as an integer over an integer, we can refer to that number as a rational number. Now, all the stuff in between that can't be written as a fraction, we refer to those as irrational numbers. Things that are irrational. Non-terminating and non-repeating decimals. If we have a decimal number that terminates, it can be written as a fraction. It's rational. If we have a decimal that repeats, it can be written as a fraction. It's rational. But if we have a number, a decimal that's non-terminating and non-repeating, it cannot be written as a fraction. It is irrational. For instance, pi. Pi is 3.141592653588979, and it goes on and on and on forever, without end, without repeating. Pi would be an example of an irrational number. If we take the square root of a perfect square, like 25 or 81, the square root of 25 is 5. 5 can be written 5 over 1 as a fraction. Square root of 81, that's 9. 9 can be written 9 over 1 like a fraction. Square roots of perfect squares are rational numbers. Square roots of non-perfect squares, for instance, the square root of 2, the square root of 2, since it's not the square root of a perfect square, happens to be 1.4142, and it goes on and on and on, just like pi, forever and ever, never ending, never repeating. Square roots of non-perfect squares are irrational. They cannot be written as a fraction because they are non-terminating, non-repeating decimals. We'll take a closer look at fractions in our next lecture. So just to kind of recap our different types of numbers, we started with the natural numbers, the counting numbers. We added in 0, and that gave us the whole numbers. The whole numbers were positive integers. So when we added in the negative whole numbers, we got the whole set of integers. Then we added in things that can be written as fractions, and that gave us the rational numbers. And then we had this whole other separate category of irrational numbers, things that couldn't be written as a fraction, are non-terminating, non-repeating decimals. All of this taken together is the set of real numbers. Real numbers anything on the number line. The number line itself, which goes in both directions forever and ever, is a real number. I should say anything. I should say the number line represents all the real numbers. Anything on the number line is real. I'm going to give a set of numbers now. -2, 0, 1/4, -1.5, 112, -3, 11, square root of 2. And we're going to go ahead and list the natural numbers, the whole numbers, the integers, the rationals, the irrationals, and the real. So the natural numbers are our counting numbers. As we go through our set, the first one we come to that is a counting number is 112. We also have 11. What's the difference between natural and whole numbers? Well, if we add 0 to the natural numbers, we get the whole numbers. And there is 0 in our set. So 0 is a whole number. And then our natural numbers, 112 and 11. If we take the negatives of the whole numbers and add those in, we get our integers. -2. We already had 0. We already had 112. -3. -3 is an integer. We already had 11. All integers, remember, are also rational numbers. We can just write it as, for example, 11 over 1. And we've written 11 as a fraction, which means it's a rational number. So our rational numbers, -2 still, 0 still, new entry, 1/4. -1.5 can be written as a fraction because it is a terminating decimal. So it is rational. 112, -3, 11. And just because we see the square root sign doesn't mean it's not rational. We have to look underneath the square root and see, are we taking the square root of a perfect square? Are we taking the square root of 1, 4, 9, 16, 25, so on and so forth? We are not. 2 is not a perfect square, which means it is not rational. It is irrational. It was the only number left. Everything else was a rational number. And all of them are real numbers. We take the rationals and the irrationals together. Let's do another example. If you want, you can pause this one and try it. Natural numbers. At first glance, you might be looking through this and you might say there are no natural numbers, but you would be wrong. Because what we see here as the square root of 25 is actually the number 5. So the square root of 25 is a natural number. To get our whole numbers, we would add 0 in, but 0 is not a member of this set. So the square root of 25 is still the only whole number. Since it's a whole number, it's also an integer. Do we have any more integers? We do. Negative 15. That's it. Rational, things that can be written as a fraction. That includes all our integers. So the square root of 25 is rational. Seven thirds. Negative 15. Negative 3/4. Square root of 5, that's the square root of a non-perfect square. That's irrational. Negative 3.7, that's a terminating decimal. That is rational. And 2 over 0. It looks like a fraction, but the number one rule of math is that you can never divide by 0. You cannot have 0 on the bottom of a fraction. And therefore, 2 over 0 doesn't exist. It can't be any of these things. It's not irrational. It just doesn't exist. The only irrational number we had was the square root of 5. So our real numbers are the square root of 25, 7 thirds, negative 15, negative 3/4, square root of 5, and negative 3.7. Take our rationals and our irrationals together. We couldn't say all this time because 2 over 0 is not a real number. It does not exist because 0 on the bottom of the fraction dividing by 0. Undefined. Does not exist. Let's expand our use of the less than, the greater than, the equal sign into negative numbers. And fraction looking things. Let's do these 3 first. Negative 1 and 0. Let's look at them on a number line. 0 would be over here. Negative 1 would be over here. Since negative 1 is to the left of 0, to the left is less than. In this second one, 14 over 2, 14 halves. That's a division problem. 14 divided by 2. 14 divided by 2 is 7, which means these are both 7. Equal would be the appropriate sign. And again, let's take a look at the number line for negative 5 and negative 6. We'd have 0, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. They would fall in this order. Negative 5 is to the right of negative 6. Negative 5 is greater than negative 6. Remember, number line order always would have less than in between. So the little pointy end points to -6. The big open end points to -5. It gives us the greater than symbol. Three more. Feel free to pause and try these if you want. I'm going to get started. Looking at the number line. Three falls to the right of 0. 0 is to the left of 3. 0 is less than 3. Number line order is always less than. -5 is over on the negative side of the number line. 15 is over on the positive side of the number line. 15 is to the right. 15 is greater than -5. Again, number line order is always less than. Little point points to the -5, big open end with the 15. Gives us the greater than sign. The fraction 12 over 4, that's a division problem. 12 divided by 4 is 3. These are both 3. Equals is what goes in. Now I want to talk about something called absolute value. Absolute value means distance from 0 on a number line. And since distance is always positive, absolute values will always be positive. The only exception is that sometimes it can be 0. If we want to visualize absolute value, the symbol we use is 2 vertical bars. Let's look at the absolute value of -2. -2 is 2 units from 0. 1, 2. So the absolute value of -2 is +2. Let's say we were looking for the absolute value of +3. Well, 3 is 1, 2, 3 units away. The absolute value of +3 is 3. Now, surely by looking at these 2 examples, you can see our easy way of doing absolute value without thinking of the number line. Just make it positive. Absolute value is the make it positive function. The absolute value of -2 is +2. The absolute value of +3 is +3. Always make it positive. Our exception, the absolute value of 0. How far away from 0 is 0? We're already there. We're 0 away. Absolute value of 0 is 0. So the absolute value of a negative number is the positive version. The absolute value of a positive number is the positive version. The absolute value of 0 is 0. And this works for fractions and decimals too. There's nothing special about the counting numbers, the whole numbers, the integers. The absolute value of 5.6 would be 5.6. The absolute value of -4/7 is +4/7. We see a negative number in the absolute value sign, all we do is make it positive. I'm going to put 5 more examples of this up. Feel free to pause and try. Okay, let's do these 5. The absolute value of a negative number is the positive version. So the absolute value of -8 is 8. The absolute value of a positive number is itself. Absolute value of 9 is 9. Absolute value of a negative number is the positive version. The absolute value of -2.5 is +2.5. Absolute value of a positive number is itself. Absolute value of 5/11 is 5/11. The absolute value of a negative number is the positive version. The absolute value of -1/2 is +1/2. Let's go back to those problems where we have to pick less than, greater than, or equals. This time, let's start involving the absolute value signs. So less than, greater than, or equal. We have to take the absolute value of 0 to check. Absolute value of 0 is 0. 0 is less than 2, which means the absolute value of 0 is less than 2. Let's compare the absolute value of -5 with 5. Well, the absolute value of -5 is +5, and 5 equals 5. So the absolute value of -5 equals 5. This one's a little tricky. We're comparing the absolute value of -3 with the absolute value of -2. Now, -3 would be less than -2, but it's not necessarily the same for the absolute values. The absolute value of -3 is +3. The absolute value of -2 is +2. 3 is greater than 2, which means the absolute value of -3 is greater than the absolute value of -2. The absolute value of 5 and the absolute value of 6. The absolute value of 5 is 5. The absolute value of 6 is 6. 5 is less than 6. So the absolute value of 5 is less than the absolute value of 6. The absolute value of -7 and the absolute value of 6, we're comparing. Well, the absolute value of -7 is +7. The absolute value of 6 is 6. 7 is greater than 6. So the absolute value of -7 is greater than the absolute value of 6. Five more, then we're done. You are welcome to pause and try these if you want. Okay. The absolute value of 8 is 8. The absolute value of -8 is 8. These are equal. So those are equal. The absolute value of -3 is 3. 0 is 0. Not even an absolute value there. 3 is greater than 0. So the absolute value of -3 is greater than 0. Absolute value of -7 is +7. Absolute value of -11 is +11. 7 is less than 11. So the absolute value of -7 is less than the absolute value of -11. Absolute value of 3 is 3. Absolute value of 2 is 2. 3 is greater than 2. So the absolute value of 3 is greater than the absolute value of 2. Absolute value of 0 is 0. Absolute value of -4 is +4. 0 is less than 4. So the absolute value of 0 is less than the absolute value of -4. Okay, that's it for this one.